catalogue. The orbital calculations converged on an eccentricity far greater than 1, near 6.1 to 6.2. That number was a mathematical announcement. This object was not bound to our Sunday. It was passing through with a speed of nearly 60 kilometers per second, in a universe where many things circle patiently. For a while, the world treated it like the other two interstellar guests we had seen before. But even early on, there were strange notes in the score. James Webb, peering with its deep sensitivity, recorded spectra of its coma. The composition was not dominated by water vapor, as is typical for comets formed in the cold outskirts of our system. Instead, the signature was unmistakably strong for carbon dioxide. That chemical voice suggested a birth environment unlike ours. The visitor was not merely alien by origin, it was alien in the way it held heat and released breath. The weeks unfolded like a slow experiment. In early October, on the 3rd, the object paid a close call to Mars. Radio and optical tracking from spacecraft and ground stations confirmed that it was exactly where the orbital predictions put it. The trajectory calculated from those data matched the predicted path with an almost unsettling steadiness. Then the geometry of the system shifted. From our vantage, the object moved behind the Sun in superior conjunction, an interval when direct optical observation becomes impossible for a time. Astronomers call it a blind spot. During that conjunction, the Sun itself became unusually active. On its far side, energetic events erupted. 3 major coronal mass ejections launched in sequences whose timing and trajectories traced lines that were, by coincidence or by a deeper ordering, roughly aligned with the path where our interstellar visitor was passing. Coronal mass ejections are vast expulsions of plasma and magnetic field, giant storms of charged particles that sweep across space and can buffet planets and spacecraft. The record books held examples of comets being battered by solar storms, their tails momentarily distorted, their dust plumes rearranged. Physics teaches us that when an object in space receives a substantial plasma wind, it can perturb its orbit because plasmas interact with material, exert drag, and shuffle charges in ways that ultimately produce forces. In other cases, an impulsive event can be detected as a small deflection or a measurable change in velocity. The expectation was straightforward. When superior conjunction ended and 3I, Atlas reappeared, telescopes around the world leaned in to see what damage had been done or what tug had been felt. The surprising and now famous fact appeared in the numbers. The object had emerged without measurable deflection, no deviance in position, no change in speed, no significant alteration of trajectory. The orbit fit remained the same within the margins of error. For a body that had just experienced the passage of 3 strong CMEs, that steadiness read like a gentle defiance of simple expectation. What are we to make of such steadiness in the face of solar storms? There are immediate, cautious possibilities grounded in known physics. Perhaps the geometry of the CMEs and the object's orientation created a scenario where the net impulse was minimal. Plasmas and magnetic fields are directional. If the CME struck the object at angles that yielded symmetric forces, or if the object's own outgassing produced balancing jets at the right moments, measurable deflection could be small. Alternatively, if the nucleus were large enough and dense enough, the momentum transferred by the passing plasma might be insufficient to produce a detectable orbital perturbation. A massive, compact body resists nudges, much as a heavy ship resists small waves. But the data painted a more complex picture. Remember how Webb's spectrometer recorded a CO2-dominated coma? And recall how earlier observations showed significant, non-typical behavior in composition. Those clues made the simple mass-based answer unsatisfying. If this object's composition and surface interaction with radiation were unusual, perhaps its interaction with the Sun's plasma environment was also unusual. Some scientists began to consider electromagnetic effects with renewed seriousness. After all, the Sun is not merely a gravitational source, it is an enormous magnetic dynamo whose winds carry charged particles and entwined magnetic fields. Interactions between magnetized plasma and conductive or charged bodies can produce forces that are not purely drag in the classical sense. In the quiet hum of control rooms and conference calls, researchers sketched scenarios. Could the nucleus support a sheath of charged particles? Could it have a magnetized region, perhaps generated transiently by currents in its coma, that reoriented local field lines and altered how plasma flowed around it? A magnetic interaction could do more than buff a comet. It could isolate it from the bulk flow of the CME, channeling charged particles along field lines instead of allowing them to strike the body directly. In that sense, the comet could present a kind of transient electromagnetic shield, not because it had an intrinsic magnetic core akin to Earth, but because the dynamics of charged dust, ionized gas, and local currents conspired to alter the effective boundary between the CME and the nucleus. Then there is the provocative idea that elements of the object's activity could have been not only reactive but proactive. Some papers, cautious and rigorous in tone, raised the possibility that the interaction was reciprocal. Perhaps the comet's presence perturbed the solar magnetic environment in ways that made the Sun more likely to release CMEs directed along certain trajectories. This is not to say that a small body commands the Sun like a puppeteer. The energy scales are enormously different. Yet plasma physics is subtle, and under certain conditions, small perturbations to field topologies can seed instabilities that grow. Consider a stream of ionized particles encountering a region where magnetic connectivity is marginal. If the local field configuration is delicate, a perturbation might tip the balance and precipitate a larger scale release. In this way, a comet crossing the heliospheric current sheet at a vulnerable point could, hypothetically, play a role in the timing or directionality of a CME. Speculation like this must be treated with discipline. The standard scientific response is to test hypotheses with data. Given the sparsity of direct measurements while the comet was behind the Sun, researchers relied on indirect evidence, time-stamped solar observatory data, coronagraph imagery, magnetogram readings, and the later, unperturbed orbital fit. They combined these datasets to construct models of the CME trajectories and their overlapping regions with the comet's projected path. Some models suggested that the CME fronts intersected the comet's position at times that would have produced interaction. Other models left open windows in which the comet might have slipped through less disturbed regions. The uncertainties were real and stubborn. What made the whole episode fascinating was that the comet's behavior, taken together with its composition, hinted at a category of interstellar objects that might respond to stellar environments differently than our models predict. If a body's coma is rich in ionizable constituents like CO2, and if the dust grains are small and electrically active, then the collective plasma response around the nucleus could be markedly different from that of a typical water-ice-dominated comet. Charged dust can form complex structures in a plasma wind, and those structures, in turn, can influence the way magnetic fields wrap and reconnect. The net effect might be to cushion the nucleus from the worst of a CME's direct impact. Over weeks and months, teams across multiple continents ran simulations. Computational plasma physicists fed composition profiles into magnetohydrodynamic models, tuning dust grain sizes, charge-to-mass ratios, and coma densities. Some runs produced neat outcomes, a self-organized sheath of charged particles forming a buffer zone that redirected incoming plasma. Other runs failed to produce significant protection. The results depended sensitively on poorly constrained variables, like the true size distribution of dust grains and the rate at which neutral gases were ionized by solar ultraviolet light. That sensitivity was a sobering reminder of how much we still have to learn about small body plasma interactions. Beyond the equations and the simulations, the event had a human rhythm. Nights at observatories lengthened with the cadence of data downloads. Scientists in different time zones triangulated their analysis, each group bringing a different specialty: orbital dynamics, solar physics, spectrometry, dust modeling. Graduate students wrote scripts to mine terabytes of telemetry. A postdoctoral researcher in Europe spent several caffeine-blurred nights comparing magnetometer readings with orbital residuals, searching for even the faintest correlated signature. When preliminary results were shared in teleconferences, the tone was both weary and exhilarated. Anomaly invites attention. Attention invites collaboration. The comet had done what anomalies do best. It catalyzed a widening of inquiry. Public discourse followed its own path. Some reports sensationalized the idea that the comet was somehow impervious to harm, or that it possessed unusual powers. Responsible communicators emphasized nuance. The evidence supports unexpected steadiness and suggests plausible electromagnetic interactions. It does not demonstrate sentience or exotic technology. Yet even this tempered explanation ignited curiosity. Teachers incorporated the episode into lessons on magnetism and plasma in solar system contexts. Amateur astronomers shared images, and artists rendered the comet's passage in hues of blue and copper, imagining its charged sheath as an aurora in miniature. As months stretched into a year, the broader implications came into focus. If interstellar objects can interact with stellar magnetic environments in complex ways, then their influence extends beyond mere passage. They become probes of stellar wind structure and magnetic topology. Each interstellar visitor carries a record of its birth environment. But it also acts as an active test of how small bodies behave when exposed to alien stellar conditions. In this sense, 3I, Atlas, was both messenger and instrument, revealing both its own nature and the character of our star's outer layers. Researchers proposed follow-up strategies. If another interstellar object were detected approaching a star, early detection would be vital to place more instruments in position before conjunctions or solar occultations. Missions were discussed in planning rooms. Flyby spacecraft carrying magnetometers, dust analyzers, and plasma spectrometers could, in principle, resolve the ambiguities that remote observations cannot. For now, our astronomy would have to extract maximum information from light curves, spectra, and the quiet shifts of orbital fits. There is a poetic symmetry to how science responded. The very thing that moved through our system without being captured by its gravity, an object that had no business stopping, captured our attention and kept it for a long while. Its passage was short on cosmic timescales, but long enough for us to refine questions, sharpen instruments, and re-examine assumptions. It taught us that the heliosphere is not merely empty space where gravity rules supreme. It is a sea of charged currents and magnetic eddies, where small bodies can experience interactions that are subtle and, sometimes, surprisingly stabilizing. Tonight, as you settle deeper into sleep, imagine the scene. Picture the comet's small nucleus, a dark kernel of ancient material, trailing a luminous, carbon dioxide-rich veil. Around it, imagine not only dust and gas, but a dynamic, changing sheath of charged particles, an ephemeral cocoon that whispered and shifted as solar wind and CME fronts swept by. Think of the sun, enormous and tempestuous, casting off huge bubbles of plasma, and picture this tiny traveler threading through those storms like a leaf on a river that, for a brief time, finds a channel that keeps it unturned. We do not yet have all the answers. Perhaps in later years, when another interstellar visitor arrives and our instruments are prepositioned, many of these questions will be settled. Perhaps new physics will remain out of reach, replaced instead by more refined models of dusty plasmas and ionization chemistry. Either way, 3I Atlas has left us with a memory. The universe sometimes arrives cloaked in puzzles. Our best response is patient attention, careful modeling, and a willingness to be surprised. Allow your breath to slow now, and let the wonder settle in your chest like a warm stone. You have listened to the whisper of a comet that came from elsewhere and, in passing, asked us to listen harder. The night is quiet. Observatories sleep. Instruments rest. But the questions remain, and they are soft companions for the dreaming mind. Good night, dreamer. Good night, bedtime universe. Until the next story, may your curiosity carry you gently into sleep. Hello, dreamers, and welcome back to Bedtime Universe. Before we begin tonight's journey, I want you to take a moment and tell me, where are you watching from tonight? What time is it? Where you are? Maybe it's midnight, and the city outside your window has fallen quiet. Maybe it's morning, and the first light of dawn is brushing softly against your walls. Wherever you are, whatever time it may be, you are here now, and that's all that matters. So take a deep breath. Let it travel slowly through your chest. Exhale everything that weighs you down. You are safe here, floating in a quiet sea of starlight. Because tonight, we're leaving Earth behind. We're crossing the solar winds, past the orbit of Mars, past the cold glow of Jupiter, and into the dark places where sunlight fades. There, beyond the reach of any planet, something ancient has entered our sky, something that doesn't belong to us. A traveler, a fragment of another world, a messenger from the farthest corners of the galaxy. Its name is 3, the third interstellar wanderer ever known to visit our solar system. It came quietly, sliding through the blackness of space with the patience of eternity. For billions of years, it drifted unseen, a frozen memory of a star long forgotten. No light, no warmth, no voice, only silence, and the whisper of cosmic dust sliding past its ancient surface. Astronomers believe it was born in the thick disk of the Milky Way, a vast, old region filled with the quiet ghosts of ancient sun. Maybe it was once part of a planet, shattered and thrown away by a distant star's gravity. Maybe it was ice from the edge of an alien world, a shard of frost that escaped into the interstellar dark. Whatever its origin, 3I Atlas became a wanderer, drifting alone through the endless gulf of time. And then, by chance or fate, it found us. In May of 2025, a faint light appeared in the data of a telescope called TESS. At first, it was nothing more than a point, small, dim, and moving far too fast. But it caught someone's eye, a pattern that didn't belong. By July, the automated system known as Atlas confirmed the discovery. This wasn't an asteroid. It wasn't even a regular comet. Its path was hyperbolic, a perfect curve that meant one thing. It didn't come from here. It was an interstellar visitor. Scientists named it 3I Atlas, the third interstellar object ever found, after Oumuamua and Borisov. But this one was different. It was larger, almost 6 kilometers across. It was faster, 58 kilometers every second, and its path lined up almost perfectly with the plane of the planets, only 3 degrees away, as if it had been aiming for us all along. Some called it coincidence. Others whispered that maybe, just maybe, There was something intentional in its arrival. As 3I Atlas approached, the sun began to awaken something inside it. Its surface, once frozen solid for billions of years, started to crack. Ice turned to vapor. Gas rushed into space, and the traveler began to breathe again. A faint halo called a coma surrounded it. A tail of dust unfurled behind it, stretching like a luminous ribbon through the void. And with every passing hour, it grew brighter. But something strange was happening. The brightness wasn't just rising as expected. It was exploding, 5 times stronger than astronomers predicted. The comet was alive with activity, its core boiling with energy, as if something deep within was awakening for the first time in eons. Its light also behaved differently. When scientists measured its polarization, the way light waves scatter and twist, they found something extraordinary. Negative polarization, the strongest ever seen from any object in space. That meant its dust, its ice, its very material, was nothing like anything formed in our solar system. It was truly alien, a signature of a world that orbited another sun. In late October 2025, the traveler reached its closest point to the Sunday, October 29th, just 1.4 astronomical units away, a little inside the orbit of Mars. For a moment, it shone brighter than anyone imagined. A beacon of silver-blue light stretched across the deep black sea of space. The sun's radiation carved glowing streams from its body, and the comet answered by glowing even more fiercely, as if it wanted the universe to remember it. Telescopes across the world turned toward it. Data streamed in from observatories in Hawaii, Chile, Spain, each one capturing fragments of its farewell. And then, like all wanderers do, 3I Atlas began to fade. The coma dimmed. The tail thinned until it disappeared completely, and the traveler turned back toward the darkness, a silent ember drifting away from our sun, forever beyond the pull of its gravity. Now, 3I Atlas sails once more through the interstellar night. It will not return. It will drift among the stars for billions more years, crossing the void between constellations, passing the cold shadows of alien worlds, gliding silently through the fabric of time. No one knows where it will go next. Perhaps it will slip past another star one day, and to someone else, on another planet, under another sky. It will appear as a faint streak of light, a mysterious visitor, just as it did to us. And maybe, on that distant world, someone will look up and wonder, where did it come from? Who once watched it pass before? As you close your eyes tonight, try to imagine it. A small, ancient comet, floating in the black, its icy surface glittering faintly under a field of infinite stars. No sound, no rush, only peace. It has seen things older than memory itself. It carries within it atoms born in long-dead suns, elements that once burned bright and then faded into silence. It has traveled across the Milky Way, past collapsed stars, nebulae, and clouds of dust that glow softly in the ultraviolet light of newborn systems. And yet now, for a brief moment in eternity, its story has touched ours. You and I, lying here, breathing under the same night sky, are part of that same vast story. The story of things that move through darkness, seeking light. So breathe slowly. Let your thoughts drift outward, past the moon, past the pale shimmer of Mars, past the cold rings of Saturn and the quiet ice of Neptune. Beyond all of it, the stars begin to open like a sea of lanterns. That's where 3I Atlas is now, silent, steady, and free. And maybe, in its long journey through the dark, it carries with it the echoes of this very moment, the sound of your breath, the calm of your heart, and the faint, fragile thought that somewhere out there you are connected to something infinite, Sleep softly, traveler of the earth. Breathe deeply. Let go, because somewhere beyond the veil of light, a wanderer continues its voyage through eternity. And tonight, you travel with it. Good night, traveler. Good night, dreamer. Until the next story. Hello, dreamers, and welcome back to Bedtime Universe. Tonight we will drift together into a quiet corner of the cosmos, a place where curiosity hums softly and the sky keeps its secrets like whispered stories. Make yourself comfortable. Breathe in slowly. Breathe out slowly. Let the day loosen its grip and allow your thoughts to unfurl like thin ribbons of starlight. This is the story of a visitor from beyond, a small, cold messenger that crossed the vast darkness between stars and, for a brief while, threaded itself into our sky. Scientists call it 3-Eye Atlas. To many, it has become a puzzle. To some, a warning. To others, a doorway. Tonight, we will walk that doorway together, slowly and gently, listening to the strange hints it left behind. Long before our sun kindled, before our oceans gathered on an infant Earth, this object was already on its way. Imagine a world of distant suns, a disk of dust and gas circling some ancient star. Somewhere in that pale, crowded neighborhood, an ice fragment formed. It lived a quiet existence as part of another system. Then some violent event sent it adrift. Over time so vast, they make human memory feel like a single blink. That it crossed the empty dark, carried on the indifferent currents of the galaxy. That was its first long sleep. Then, in our era, in the small window of human attention and telescopic looking, telescopes noticed a faint motion. It showed up in the regular feeds and alerts, a dot moving with an unusual speed and path. The networks named it 3-Eye Atlas. The first two had already taught us to be humble, but this one arrived with riddles that were sharper and stranger than anyone expected. At first glance, the numbers were puzzling. Its trajectory was hyperbolic, which means it was not bound to our Sunday. It came from far beyond, on a one-time crossing. It moved in a retrograde direction, traveling opposite the familiar sweep of the planets. Yet its orbit lay almost along the same plane that the planets occupy, inclined at only about 5 degrees. That combination, retrograde motion but low inclination, felt statistically odd. It was as if a traveler arrived along a road parallel to ours, but going the other way. The geometry of that passage made some astronomers quiet with curiosity, because coincidences like that, if truly coincidental, are rare. If it were not coincidence, what else might the path be telling us? Further observations unfolded the stranger truths. At nearly 3 astronomical units from the Sun, at a distance where comets built in our own system usually slumber and preserve their ices, this visitor uncoiled as if waking. It released water vapor in massive amounts, when most familiar comets do nothing at all. Not just a slow drip, but a surge. The activity at 2.9 AU contradicted the expectations of ordinary cometary physics. Even more surprising, when scientists analyzed the gases in its coma, the ratio of carbon dioxide to water turned out to be exceptionally high. For every part of water, there were 8 parts of carbon dioxide. That 8-to-1 ratio is unlike anything seen in comets that formed in our cold backyard. Carbon dioxide dominated the chemistry of this strange halo of gas. The spectrum of light the object reflected told another story. It was not simply bright or dim, but it polarized light in ways that did not match known cometary behavior. Polarimetry, measuring the oscillations and directions of light waves, revealed anomalies. The patterns suggested unusual dust geometry, perhaps grains with internal structures or surfaces that scattered light in unfamiliar ways. The polarization signatures bore a negative extremity and phase angle changes that defied standard models. When faced with such data, astronomers do what they always do. They measure again. They cross-check instruments. They test for error. The anomaly persisted. And yet, one more disquieting paradox emerged. When large amounts of gas are expelled from a small body, physics dictates a recoil. Gas jets act like microscopic thrusters. Over time, they nudge an object off a purely gravity-determined orbit, producing measurable non-gravitational acceleration. This is well known and accounted for in cometary dynamics. But the non-gravitational acceleration measured for 3I Atlas was far weaker than the observed prodigious gas release should have produced. The magnitude of the gas flux suggested a stronger push. Instead, the object seemed stubbornly steadfast, barely perturbed. This mismatch created a tension between observations that demand explanation. On one side, large gas emissions, extreme CO2 dominance, odd polarimetric behavior, a retrograde, hyperbolic orbit with a low tilt. On the other, a weak, non-gravitational acceleration inconsistent with the scale of outgassing. If the outgassing were real at the observed scale, the body must be much more massive and thus larger than some estimates allowed. If it were massive, how could it have formed with such an unusual composition and surface behavior? If it were small, why was it not being accelerated? Estimates for the size of its nucleus varied wildly. Some analyses suggested a compact body less than half a kilometer across. Others allowed for diameters up to 5 or 6 kilometers. The difference between those numbers is not small. It changes mass and inertia by enormous factors and flips the calculations that follow. When scientists encounter such a thicket of contradictions, they must do what science exists to do: gather more data, broaden hypotheses, and be willing to consider uncomfortable possibilities. The most conservative approach is to imagine that 3I Atlas is an extreme yet natural variant of cometary physics. Perhaps it formed in a region of its parent system where volatiles other than water accrued preferentially. Certain formation environments could produce cores rich in carbon dioxide, with layered structures that release gases in unusual bursts. Perhaps the internal porosity or compactness is different, trapping or channeling gas in a way that changes the effective thrust. Perhaps rotational dynamics spread jets in directions that cancel net impulse. Each of these is plausible and can be folded into models, though with significant adjustments. A more daring line of thought moves into deeper waters. Some researchers whispered of a black swan event in astronomy, an occurrence so rare and consequential that it forces the revision of assumptions and frameworks. The term black swan had traveled into astrophysical discourse because, sometimes, unpredicted anomalies have reshaped how we think about the natural world. Could 3I Atlas be such a moment, nudging us toward new understandings of material behavior, of small body dynamics, or perhaps even of physical law at particular scales and configurations? This is not to suggest headline-grabbing claims about broken gravity or overturned relativity. Science does not leap to such conclusions lightly. Instead, the suggestion is more measured. Maybe there are processes, combinations of microstructural geometry, phase change dynamics, and radiative interactions that are not yet captured by our current models. Maybe on the surface of 3I Atlas, microscopic layering, exotic ice phases, or mineral coatings produce behaviors that defy the simplified assumptions built upon solar system observations. Or perhaps there are kinds of feedback between surface chemistry and gas release that, under particular conditions, create near cancellations of thrust on macroscopic scales. These ideas remain speculative until they are tested. but they are worth considering because the alternative, ignoring the mismatch, would be to stagnate. Meanwhile, the human side of this story plays out with a mix of methodical diligence and restrained imagination. Observatories across the globe trained instruments on the visitor. Radio telescopes listened for molecular lines. Infrared arrays mapped thermal signatures. Polarimeters tracked the strange polarization. Teams coordinated observation schedules in near real time, aware that the window for meaningful data would not last forever. In the quiet nights of observatories, technicians adjusted filters and recalibrated detectors. Graduate students wrote scripts to sift terabytes of data. Senior scientists organized teleconferences at odd hours. It was, in many ways, a classic example of how modern science answers the call of a rare phenomenon, with cooperation, redundancy, and patience. At the same time, communities of amateur observers contributed images and time series that filled the gaps between professional facilities. Citizen science platforms aggregated visual confirmations and photometric data. Each new spectrum and photometric curve fed into global databases. Models were adjusted, then tested. Some parameters tightened, others remained obstinately uncertain. Uncertainty, here, was not a failure. It was the currency of honest knowledge. Public communication became a tightrope. In a world where every unusual astronomical headline can be amplified into sensational claims, scientists and communicators worked carefully to distinguish robust results from preliminary speculation. The press wanted stories, and the public wanted wonder. Both were valid, but fidelity to nuance was essential. Researchers were cautious to say what the data truly supported. Anomalies were present, they were significant, and they invited deeper study. Beyond that, the community avoided leaps. Speculation about black swan scenarios was framed as a useful intellectual exercise, not as a declaration of revolutionary physics. Within the labs and online forums, different narratives emerged, like competing constellations in a dark sky. They pointed to known chemical processes and proposed that the CO2 dominance could be a formative signature, reflecting a birthplace with different temperature histories and volatile reservoirs. If so, then 3I, Atlas, is a message about diversity. Planetary systems can produce bodies with substantially different volatile budgets, and our models must be flexible enough to embrace them. Others focused on morphology. If the nucleus were highly structured, with massive subsurface cavities, or an asymmetric distribution of volatiles, the outflow could be more complex than a simple rocket effect. Jets could be balanced by counterjets, or the geometry of mass loss could distribute momentum in ways that net to small acceleration. Laboratory experiments and computational models began to explore three-dimensional porosity and jet dynamics at scales relevant to cometary nuclei. These endeavors required time, but they also yielded insights that could be applied to future encounters. Then there were the theorists who considered more exotic but testable physics. They did not stake their reputations on overturning pillars, but they examined whether known laws might permit subtle, scale-dependent effects under unusual compositional or structural regimes. They asked if phase changes involving clathrate ices or complex organics could lead to delayed or buffered outgassing. They calculated whether radiative torques or photophoretic effects could conspire to counteract the direct momentum transferred by jets. These models were complex, layered, and, crucially, falsifiable. That made them worthy of attention. All hypotheses required better constraints on basic numbers. The wildly varying estimates of nucleus size were a particular problem. A 5-kilometer core and a 300-meter core imply orders of magnitude difference in mass, and therefore in how the object would respond to any thrust. Pinning down size required clever analysis. combining thermal emission measurements, limits from brightness, scattering properties from polarimetry, and dynamical fits that accounted for possible non-gravitational forces. It was painstaking work, and it highlighted how a single parameter of uncertainty can ripple outward into many interpretive paths. As people around the world looked up, small human stories accumulated like stardust. Teachers used the anomaly as a lesson in science clubs. Poets wrote short lines about an ancient messenger slipping silent through the night. Children asked questions that prompted simple, honest answers. Why does space have different kinds of comets? Could something like this happen again? The emotional resonance was gentle too. There was a shared sense of being part of a living inquiry. The public learned how science contends with surprises by being systematic, skeptical, and open to revision. In the end, 3I Atlas may turn out to be a deeply instructive oddity that teaches us about the diversity of planetary systems. It may be a case study in how early formative environments shape volatile inventory and microstructure, or, in time, it could expose processes that require extensions to our current models. Whatever the final verdict, the encounter is already valuable. It has focused attention on the need for rapid, coordinated observation strategies for fleeting interstellar visitors. It has highlighted the importance of cross-disciplinary work, combining observational astronomy with laboratory astrophysics, advanced modeling, and comparative planetology. There is a quiet lesson in the way this story unfolded. The universe does not owe us simplicity. It may occasionally present us with an object that resists tidy categorization, demanding patience and humility. That resistance, strangely, is not an obstacle to wonder. It is the engine of knowledge. When an anomaly appears, the right response is not to rush to conclusions, but to widen the aperture of inquiry, to bring more eyes to the sky, and to sharpen our instruments and our questions. So as you allow sleep to come, picture 3I Atlas sliding further into the velvet of interstellar space. Imagine it as an ancient traveler that carries within its frozen heart the chemical memory of another star. It moves forward, indifferent to our theories, but intimately entangled with our curiosity. We will continue to watch, to measure, to calculate, and to wonder. We will return to its story as more data come in. And with every new piece of evidence, our map of the cosmos becomes a little more elaborate and a little more true. Breathe in, breathe out. Allow the questions to rest for the night. Remember that uncertainty is part of the beauty of science. It is the seed of future certainty, the quiet engine that pulls us gently forward. Tonight, in the shadows under the same sky where an interstellar wanderer once sped by, you are connected to a long chain of observers. Those who listen, those who measure, and those who imagine. Good night, dreamer. Good night, bedtime universe. Until the next story, may curiosity lightly guide your sleep. Hello, dreamers, and welcome back to Bedtime Universe. Before we begin, take a gentle breath. Let the cadence of your breathing find an easy, slow rhythm. If you like, tell me where you are watching from and what hour it is where you sit. No matter the place or the time, you are here now, and tonight we will travel together into a quiet pocket of the cosmos, where one small visitor changed how we listen. This is the story of 3I Atlas, an interstellar wanderer whose passage through our sky felt at first like a whisper, then like a question. It is a tale of precise measurements and patient nights in observatories. It is also a story about how the unexpected can nudge a whole community of scientists toward new ways of seeing. We will move slowly, with the gentleness of someone tracing constellations with a fingertip. We will follow the object's path, the data it left behind, and the ripple of curiosity that spread from observatory to observatory. There will be technical moments, and there will be quiet ones. Both are part of the same night. The discovery was simple, at least in its beginning. On July 1st, 2025, a telescope in Chile called Atlas tagged something faint and moving. The pipeline flagged an object that did not belong to the known catalogue. The orbital calculations converged on an eccentricity far greater than 1, near 6.1 to 6.2. That number was a mathematical announcement. This object was not bound to our Sunday. It was passing through with a speed of nearly 60 kilometers per second, in a universe where many things circle patiently. For a while, the world treated it like the other two interstellar guests we had seen before. But even early on, there were strange notes in the score. James Webb, peering with its deep sensitivity, recorded spectra of its coma. The composition was not dominated by water vapor, as is typical for comets formed in the cold outskirts of our system. Instead, the signature was unmistakably strong for carbon dioxide. That chemical voice suggested a birth environment unlike ours. The visitor was not merely alien by origin, it was alien in the way it held heat and released breath. The weeks unfolded like a slow experiment. In early October, on the 3rd, the object paid a close call to Mars. Radio and optical tracking from spacecraft and ground stations confirmed that it was exactly where the orbital predictions put it. The trajectory calculated from those data matched the predicted path with an almost unsettling steadiness. Then the geometry of the system shifted. From our vantage, the object moved behind the Sun in superior conjunction, an interval when direct optical observation becomes impossible for a time. Astronomers call it a blind spot. During that conjunction, the Sun itself became unusually active. On its far side, energetic events erupted. 3 major coronal mass ejections launched in sequences whose timing and trajectories traced lines that were, by coincidence or by a deeper ordering, roughly aligned with the path where our interstellar visitor was passing. Coronal mass ejections are vast expulsions of plasma and magnetic field, giant storms of charged particles that sweep across space and can buffet planets and spacecraft. The record books held examples of comets being battered by solar storms, their tails momentarily distorted, their dust plumes rearranged. Physics teaches us that when an object in space receives a substantial plasma wind, it can perturb its orbit, because plasmas interact with material, exert drag, and shuffle charges in ways that ultimately produce forces. In other cases, an impulsive event can be detected as a small deflection or a measurable change in velocity. The expectation was straightforward. When superior conjunction ended and 3I, Atlas reappeared. Telescopes around the world leaned in to see what damage had been done or what tug had been felt. The surprising and now famous fact appeared in the numbers. The object had emerged without measurable deflection, no deviance in position, no change in speed, no significant alteration of trajectory. The orbit fit remained the same within the margins of error. For a body that had just experienced the passage of 3 strong CMEs, that steadiness read like a gentle defiance of simple expectation. What are we to make of such steadiness in the face of solar storms? There are immediate, cautious possibilities grounded in known physics. Perhaps the geometry of the CMEs and the object's orientation created a scenario where the net impulse was minimal. Plasmas and magnetic fields are directional. If the CME struck the object at angles that yielded symmetric forces, or if the object's own outgassing produced balancing jets at the right moments, measurable deflection could be small. Alternatively, if the nucleus were large enough and dense enough, the momentum transferred by the passing plasma might be insufficient to produce a detectable orbital perturbation. A massive, compact body resists nudges, much as a heavy ship resists small waves. But the data painted a more complex picture. Remember how Webb's spectrometer recorded a CO2-dominated coma? And recall how earlier observations showed significant, non-typical behavior in composition. Those clues made the simple mass-based answer unsatisfying. If this object's composition and surface interaction with radiation were unusual, perhaps its interaction with the Sun's plasma environment was also unusual. Some scientists began to consider electromagnetic effects with renewed seriousness. After all, the Sun is not merely a gravitational source, it is an enormous magnetic dynamo whose winds carry charged particles and entwined magnetic fields. Interactions between magnetized plasma and conductive or charged bodies can produce forces that are not purely drag in the classical sense. In the quiet hum of control rooms and conference calls, researchers sketched scenarios. Could the nucleus support a sheath of charged particles? Could it have a magnetized region, perhaps generated transiently by currents in its coma?